Hello. In this video, we are going to study the basic notions of eigenvalue and eigenvector for a matrix. So just we are given a matrix, in this case, this one that we can see in the picture, 1, 1, 1, 1, 1, 1, and 1, 1, 1. Very easy matrix, which is 3 by 3. And let us compute the eigenvalues and eigenvectors. Recall that for these two Hassans, our matrix should be square. In this case, this is 3 by 3, and it is indeed a square. So we can proceed. Our goal is computing the spectrum and describing the spectrum of a matrix, and also the eigenspaces for any lambda in the spectrum. So let us compute the eigenspectrum. So the first step is computing the characteristic polynomial, as we said in the previous video. The characteristic polynomial is just the determinant of the matrix minus lambda identity. This is just the determinant of the matrix, and observe that it's going to be almost the same matrix as we can see above. But now in the main diagonal, we are subtracting lambda. So this subtract lambda from the main diagonal is exactly the same as subtracting lambda times identity. Yeah? So this is the matrix. And now we have to compute the determinant. You have trained yourself last week in computing determinants as this one, so it shouldn't be difficult to do this. You already know a lot of techniques for computing determinants, so I'm just going to use some tricks, some easy tricks for computing this. So first I'm going to use some operations. In this case, I'm going to add to column 1, I'm going to add column 2. Then what I obtain is that the determinant is not changing. 2 minus lambda, 2 minus lambda, 2, 1, 1 minus lambda, 1, 1, 1, 1 minus lambda. And now what I can do is just to column 1 add column 3. And then what I obtain is that the determinant is the same as 3 minus lambda, 1, 1, 3 minus lambda, 1 minus lambda, 1, and 3 minus lambda, 1, 1 minus lambda. This trick is very useful sometimes, and it says that if you are just doing operations of the kind to one row, add a multiple of another row, or same with columns, then the value of the determinant is not changing. Now the following trick is that if you have a whole row or column that is multiplied by the same number, in this case 3 minus lambda, you can take this 3 minus lambda out of the matrix. So I can take the 3 minus lambda here, and then this will be the determinant of 1, 1, 1, 1, 1 minus lambda, 1, 1, 1, 1 minus lambda. Observe that the trick here is just eliminating one of the lambdas. The second trick is just again using operations. So in this case, to the second row, I'm going to subtract the first row, and from the third row, I'm going to subtract the first row. This gives us the 3 minus lambda and the determinant. And the determinant again is not changing in value, so it's going to be 0, negative lambda 0, and 0, 0, negative lambda. Once you are here, you can use a trick, or you can develop the determinant by using another techniques. But it is clear that when you have what is called an upper triangular, which is this case, observe that under this main diagonal, which is the 1 minus lambda, below this diagonal, everything is 0. This is what we call upper triangular matrix. And for this upper triangular matrix, the determinant is always, and this is very important, always the product of the main diagonal. So, as a result, this is 3 minus lambda times 1 times minus lambda and times minus lambda. At this point of the computation of the polynomial, it's a mistake trying to expand the polynomial, because in fact what we are looking for is the roots of the polynomial. So since we want the roots, and the roots are the factors, we don't need to do a lot more job. It is just writing like this. This factor 3 minus lambda. The second factor is, in fact, the 0 minus lambda, and the third one, the 0 minus lambda. This is a consequence of the fundamental theorem of algebra, that if we are in a 3 by 3 matrix, observe this point because this is important, then the degree of the polynomial is 3. Degree 3. And then the number of roots are always, well, not the roots, but the number of the roots. That's number of roots is going to be always smaller than or equal to 3. Okay, so what is the spectrum? Once we have computed the polynomial, we can already write down the spectrum. So in our case, the spectrum is just the set of the roots. And observe that the only roots that we have are the 3 and the 0. But what happens in here? The terms 3 is repeated only once, as you can see here, and but the term 0 is repeated twice. So basically, this should be expressed as follows. The algebraic multiplicity of the 3 is 1, because this is only repeated once, and the algebraic multiplicity of 0 is 2, because it is repeated twice. Okay, this is the notion that that it explained in the lesson part of multiplicities, which are very important for what we are going to study tomorrow. So right now, eigenvalues 3 and 0, they are different, but only 2. The 3 is repeated only once, and the 0 is repeated twice. Okay, once we have this is just the first stage completed. We know eigenvalues and multiplicities. Then the second part of the example is completing the eigenspaces. Eigenspaces. So for each value in the spectrum, let's compute the eigenspace. So the first eigenspace, maybe we can compute E sub A of 0. And this is the set of the vectors U such that A minus lambda times the identity, in this case lambda is 0 because this is the eigenvalue, is going to be 0. So this set is just the set of the solutions. Okay, here we need the U. So it's just A times U equals 0. This is what we call the null space, or the set of vectors U that goes to 0. And this is just the solution of an homogeneous matrix. So we consider the matrix, which is 1, 1, 1, 1, 1, 1, 1, 1, 1, and the 0, 0, 0. And we do Gaussian, as you learned last week, in order to solve the system. In order to do Gauss, we pick the first entry in the first row and in the first column if it is different from 0. And as you know, if it is not different from 0, we reorder the rows in order to obtain this non-zero entry. This number is called a pivot. And now we do zeros below. So row 2 minus row 1 and row 3 minus row 1. In this case, what we obtain is that the first row remains as it is. The second row becomes 0, 0, 0, 0, and the third row becomes 0, 0, 0, 0. So this is our system. At this stage, we can forget about the last two rows, the 0 rows, and only one row remains. 1, 1, 1, 0. And this is our pivot. Okay, so at this point, in order to solve the system, what we do is identify that we have three unknowns, the x, and the other two, the y and the zeta. And I'm going to write the y and the zeta in green, the y and the zeta, because these two variables with no pivots are going to be called free. And don't ask why, but I think in green when I think in freedom. So the three variables are the green one, and the blue one is the pivot variable. So the goal for solving this is expressing the pivot variables in terms of the three. The three, as the name suggests, are free, so they can take any value, but the pivot variable should be expressed in terms of the three. So in this case, what the equation says is that the x plus the y plus the zeta, this should be equals to 0. This is just the equation. Okay, so our goal is expressing x in terms of the x and the y, of the green one. So you can write that the x equals, and then move the y and the zeta to the other side. So in this case, minus y minus zeta. Okay, so once we have this, so once the the pivot variables are written in terms of a free variable, we are prepared to define the solution. So the subspace is a of 0 is going to be the set of the vectors x, y, and zeta. X, y, and zeta. What happens with the y and with the zeta? That they are free. So y and zeta are free. And what happens with the x? Well, I have said that this is going to be minus y minus zeta. So the vectors are the vectors minus y minus zeta, y and zeta, such that like the y and the zeta are just free among the real numbers. Okay? Okay, once we are here, the last step is very easy. Just what we want to express is this as a basis. So this gives us a basis. So the basis of this space, let's call the basis of the 0, is going to be the following. And this is going to be very easy, okay? Just if we have one free variable, we will have one vector. If we have two free variables, we are going to have two vectors. In this case, we have two free variables, so we are going to have two vectors. The first free variable will be given by the y. So let's look at the y and let's take the coefficient. So look here and pick the coefficients of the y, which are -1, 1, and 0. The 0 below is because in the third entry there is no y, so 0 y's. This will be the first vector. And the second vector is going to be the same but for zeta. So look at the same place and look for the coefficients of the zeta, which are going to be -1, 0, 1. Okay, so this is it. This is a basis for the space eigenspace associated to 0, which is, since it is generated by two vectors, this is a plane. Observe, and this is very important, that this subspace has dimension 2, because basically the algebraic multiplicity before was 2. So we expected this 2. We will be, let's say, more clear with this situation tomorrow, but for now, let us observe that it is very connected. The multiplicity of the number gives me the number of the vectors that I hope to find. In this case, these two. Okay, so in order to finish this exercise, we are just going to compute the other proper or eigenspace, which is the space associated to the 3. The subspaces associated to the 3 are going to be the vectors x, y, and theta, such that if I multiply the matrix by the x, y, and theta, I will obtain 3 times the vector. This can be easily written as before. This is just the set of x, y, and theta, such that A minus 3 times the identity times the vector is the 0. So as before, this is an homogeneous system. So I pick the matrix. The matrix is going to be the same as we had, the A. But now I will subtract the eigenvalue from the entries. So -3, -3, -3, and the homogeneous system. Okay, this can be written easily if instead of -3 we write -2. So let's write here the -2, -2, -2. And let us do Gauss. In order to do Gauss, maybe -2 is a bad pivot. So let us first just interchange row 1 with row 2. And then we obtain the 1, -2, 1, 0. Then the -2, 1, 1, 0. And finally the 1, 1, -2, 0. And let's do row operations. Row 2 plus 2 times plus 2 times row 1, and row 3 minus row 1. If you do these two operations, then the first row remains, and now this becomes 0, -3, and 3, and the last row becomes 0, 3, and -3, and 0. Okay, this is the first pivot. And now we pick the second pivot, which should be this one. You can normalize by dividing by -3, 0, 1, but in this case, sorry, it is very easy to do a 0 below. So row 3 plus row 2 should be enough. So 1, -2, 1, 0, 0, -3, 3, 0, and 0, 0, 0, 0. In a last step, we eliminate the 0 rows, and also if you want, you can divide the second row by the coefficients. So you divide by -3, the second row, and you obtain 1, -2, 1, 0, 1, -1, 0, 0, and this is the matrix. You can erase this, and maybe also that. So this is the new matrix, and now we have our pivot. This is the row echelon form. From this row echelon form, you obtain the equations x minus 2y plus theta equals 0, and y minus theta equals 0. In this case, x and y are pivot variable, and the only free variable is the theta, is the third one, which is the only column that has no pivot. So if we try to solve this, this is going to be the only free variable, and then we can solve the other. So from here, it is very easy. Just that the y equals the theta. So I already have obtained the y. And using this, I can go to the first equation, and then x is 2y minus theta. And using this, 2 theta minus theta, which is c. This is the natural way of solving these systems. Just this is called a backward substitution. So we identify the free variables and we do backward substitution. But there is a quicker way, if you prefer, which is doing an additional step here, which is what is called the Gauss-Jordan part, Gauss-Jordan, that you used last week in order to compute the inverse, for instance, which is just doing zeros above the pivots. So in this case, there is only one operation, which is row 1 plus 2 times row 2. If you do this, you eliminate the last of the zeros, and this will be 0, 0, negative 1, 0, 0, 1, negative 1, 0, and the pivots are the same. And now you have an easier equation. You can do the same. This gives you the system x minus theta equals 0 and the y minus theta equals 0, from which you can readily obtain that y equals theta and x equals theta. As you can see, you obtain the same solutions. So you can do as in the first case or as in the second, as you prefer, as you please. The important thing, once we have the vector, we have that the subspace associated to 3 is just the set of the vectors where the x is the theta, the y is the theta, and the theta is 3. So this is our set. And as I told you before, in this case, the basis associated to the 3 is just the coefficients of the free variable. So in this case, we only have one vector because we only have one free variable, and this vector is the 1, 1, 1. And that's it. So I have computed the eigenvalues of a matrix, which were 0 and 3. And then from each eigenvalue, I computed the eigenvectors. And we hope to find as many eigenvectors as the multiplicity of eigenvalue. And maybe a last trick. Last trick is the following. How can we check that what we have done is correct? If the vector 1, 1, 1 is well computed, for instance, this is an eigenvector of the 3. This is equivalent to say that if I multiply the matrix by this vector, I should obtain 3 times the vector. So let's check that this is true. So we pick the matrix A, which was 1, 1, 1, 1, 1, 1, 1, 1, 1, multiply this by the vector 1, 1, 1, which is the vector we have obtained. And if you do the product, you will obtain the 3, 3, 3, which is indeed 3 times the vector 1, 1, 1. So let's get back to the green. This is correct, and we did no mistake. This trick is very useful, but of course when we are on time. So if you are doing an exam and you have time to check, you can check this way. Okay, so this is everything for this video. In the next video, we will study diagonalization, but this will be tomorrow on Tuesday. See you.